Alright, part number 2 of our vector analysis stuff, the very dry vector stuff, is about vector operations. You will add and subtract vectors, you will multiply and divide by vectors, or multiply and divide vectors by scalars. So scalar is just a number, a whole number that we multiply and divide by. So vectors and coordinate systems, this stuff's pretty dry, I'll try to explain it. So if v equals v1, v2, which means v1 will be your x, v2 will be your y, and w equals w1, w2, two vectors are equivalent if and only if v1 equals w1 and v2 equals w2. We can see in this case that they are not equal vectors. So if we're going to add these two vectors, vector v, remember bold things are vectors. So these are actually vectors. So vector v plus w, the resultant of this, is going to equal v1 plus w1. So whatever v1 was, we're going to call v1 3 for now. We're going to call w1 its x component 2. So 3 plus 2. 3 plus 2. And we're going to call v2 1. It's 1 high. w2 we're going to call 4. So we get vector v plus w. When we add the components, it's going to be 5, 5. So when we're adding vectors, we can only add like components. Only add like components. Only add like components. And this means we can only add x's with x's. We can only add vector v's x component with vector w's x component, v1, w1. We should probably call these like vx and wx, vy and wy. So we can only add x's with x's and y's with y's. Very important. All right, k, which is a scalar. You see it's in italics, it's not bold, it's just a whole number. So k times any vector is going to be k times its x component, is going to be its x component of the vector, the resultant vector. And k times the y component is going to be its y component. So we can see here, here's our original vector v. We multiplied it by some whole number. All it did was increase v. So its new x component is k times v1, so it kind of looks like it doubled here. So we're going to say k equals 2 for this guy. So it made its x component double, because this is another v1. So v1 plus v1 is 2v1. And it looks like this guy doubled too. There's its x component. We doubled its y component. So you multiply the scalar by both the x and the y components. And if we're subtracting, same thing as addition. Vector v minus vector w equals v's x component minus w's x component, and v's y component minus w's y component. Now this could be different if we switched it to w minus v, it'd be something completely different. So order of operations is important, like how you write it is important. Sometimes you'll need to use trig to determine the length or direction of resultant vectors, which is why I teach you trigonometry, why we review it. So if you're adding together two vectors at right angles, vector A pointing north, vector B pointing east, you could use a good old Pythagorean theorem to find the magnitude of the resultant. And we usually call the resultant vector just a capital R, make sure it's bold. So if vector A is at a right angle to vector B, then the sum of the squares of the magnitude is equal to the sum of the square of the magnitude of the resultant vector, which is just the Pythagorean theorem. C squared equals A squared plus B squared. Instead of C here, though, we call it vector R. So if you use your calculator to determine the angle of this guy, so this is just another trig review. I mean, you really don't have to write anything down here. So we have a vector here. We choose a coordinate system. We see that its x component for this guy is 7 meters. Its y component is negative 5 meters. So negative 5, this guy's 7. We can find the magnitude of the resultant. The resultant's this guy. by the Pythagorean theorem. So r equals square root 7 squared plus negative 5 squared. But since it's a vector, we also need to know this angle in here. So to determine this angle, we use the tangents. So the inverse tangent of the opposite, which is negative 5, over the adjacent, which is 7, gives us an angle of negative 35 degrees. Or if we wanted it not negative degrees, we'd measure it the whole way around, which would be 380 or 360 minus the the 35 degrees, which gives us 325 degrees. So if we want to do the cosine, we'd use this, sine that, and so on and so on and so on. You already know trig, so don't get bogged down in it anymore. So if two vectors to be added are at an angle other than 90, then you can use the law of cosines or the law of sines. I'm not going to spend hardly any time on this at all because everything we're going to do, they're going to be at right angles to each other. So if you wanted to do it though, here you go. I'm not even going to read that. You can write it down if you want, but I'm telling you, everything we're going to do is going to be right angles. You're not going to have to worry about law of sines and cosines. And there's the law of sines. In some situations it's good, but we're not going to use it. But it's still good to know. Additional vector properties: a vector can be moved in a diagram so long as the magnitude and direction is unchanged. So if we originally have our vector, there's a little axis system, and we have a vector that's like this. We can move this guy wherever we want as long as it's still pointing this way and still has the same length. So we can go ahead and move it down to the origin, because that's what we like to do in physics, put everything starting at the origin. So as long as the length is the same, as long as this angle is the same, we can go ahead and move it around. Vectors can be expressed as ordered numbers, polar form, which you guys aren't going to have to worry about unless you do Calculus 3 in college, or in unit vector form, which is something else if you take physics in college. It's like a I, J, and K. You've probably seen this in math too. And vector subtraction may be accomplished by multiplying subtracted vector by -1 and using the technique for adding. So if I have v minus w, it's the same thing as v plus -1 times w, which sometimes makes it a little easier to see what's going on. So for example, if w equaled -3 times 5, if we multiply that by -1, we would get 3 comma -5, and that'd be a lot easier to add to v. So vectors are added or subtracted according to the rules for ordered pairs. Ax comma ay minus bx comma by. Same thing as in math class of doing when you're doing adding points in a graph. So if a vector a, remember I told you, probably should use a different color than green, huh? If we have vector a, sometimes when I'm writing it on the board or on these, I'll put a line over it. The same thing as bolding it. It means it's a vector. So here's its components. It's got an x component and a y component. There they are. So b has x and y components of -1.6 and 2.9. That means a plus b is going to equal 4.2 plus a -1.6. That's going to be its x component. And its y component is going to be -1.5 plus 2.9. So 4.2 minus 1.6, so it's going to be, it's y. So all that is going to equal 4.2, 3.2, 2.2. 2.2, comma, it's 1.5, 1.4. So this, since we're looking for the resultant is going to equal this. And we're going to express that as components of it. So Rx, comma, Ry. Here's Rx, and here's Ry. So those are the components of our resultant vector. Finding the magnitude of the sum of two vectors. So here's just a quick little problem. Find the magnitude of the sum of a 15 kilometer displacement and a 25 kilometer displacement when the angle between them is 90 degrees and when the angle between them is 135 degrees. So first you're going to sketch the two displacement vectors A and B and the angle between them. So there's a vector and there's the angle in between them. So we're going to, looks like we're going to do the 135 first. 135 degrees. When the angle is 90 degrees, we can use the Pythagorean theorem. Makes it a lot easier. In solving for r, remember to take the square root of both sides. We don't want r squared, we want just r by itself. So we substitute all this stuff in. We get r equals the square root of 25 squared plus 15 squared, which we get is 29 kilometers. That was too quick for you. There it is again. And now it's gone again. And we can use the law of sines, or sorry, this one's the cosine one. Plug all your numbers in there, and you get 37 kilometers. Again, that was too fast. Like I said though, not to worry about the law of cosines. Or we can add them algebraically, and I'm going to make you guys do this. You're going to have this one problem to rule them all, like the Lord of the Rings kind of thing. It's going to be all kinds of different vectors, and you got to add them all up. So two or more vectors, A, B, C, etc., may be added by first resolving each vector into its x and y components. So what that means is we find AX, we find AY, we find BX and BY, we find CX and CY. Then we add all the x's, and we add all the y's, and we get our resultant. So our vector, the resultant, is going to equal r x comma r y, which equals, in this case, ax plus bx plus cx comma ay plus by plus cy. And this is basically what I just wrote out. Clear that guy. So the x components are added to form the x components of the resultant. Similarly, the y components are added together to form the y component of the resultant. So vectors can be multiplied in two ways. Dot product results in a scalar. Cross product results in another vector. We're really only going to do the dot product vectors. So C equals A dot B, stuff like that. Actually, I don't think we're going to do any of this at all. I might throw it in there as a bonus. So if you can do this, I'll make it a little bonus on your quiz or test or something. All right, because Rx and Ry are at right angle, the magnitude of the resultants can be calculated using Pythagorean theorem. So when you add all these components up together, you're just going to get an x component and a y component. And you can find the magnitude by the Pythagorean theorem, and you can find the angle by using any of your trig functions. So to find the angle of direction of the resultant, recall that the tangent of the angle that the vector makes to the x-axis is given by the following. Oh, it's really hard to see. Theta equals tangent inverse of the opposite, which in our case is going to be the Ry over the Rx. The angle of the resultant vector is equal to the inverse tangent of the quotient of the y component divided by the x component. So inverse tangent of the opposite over adjacent, basically what it says. So you can find the angle by using the inverse tangent key on your calculator. If you don't know where that is, I suggest you find it. So note that when tangent of theta is greater than 0, most calculators give an angle between 0 and 90 degrees. And when tangent of theta is less than 0, the angle is reported to be between 0 and negative 90 degrees. So again, this negative just means a direction. So if we have our axes and it gives us a negative angle, that means we go this way. And a lot of times in physics, we have our little compass. Ooh, like that. So we have our little compass with north, east, south, and west on it. how we express these is a little different than you might think. Sorry, that's south and west. So let's say that this angle here is negative. We're going to call it 35 degrees. So how I would say this would be, whatever the magnitude of this is, we'll just give it an arbitrary number. We'll call it 11 meters. So how I'd express this vector, this 11 meter vector, would be 11 meters at 35 degrees south of east. Because I start in the east direction, I go 35 degrees south of it, I get 11, and this is what I get. So again, 35 degrees south of east. That means south of the eastward direction. If this is the eastward direction, we go 35 degrees south of it. You can also do it according to the north and south directions. So let's say I had a vector that looked like this. And we'll say this angle here is 65. So that makes this angle in here 25. And let's just say this vector is 9 meters per second. So there's two different ways that I can express this vector. I can say 9 meters per second at 65 degrees. This is east. This is 65 degrees north of it. So at 65 degrees north of east. Or I can also say 9 meters per second at 25 degrees east of north, which means east of the north direction. East of north. There's different notation you might see in different books. This is the one that I'm most familiar with. Actually, my students this past summer taught me this guy. I actually really like it. So both the same, two different ways I can give the coordinates of this vector. I could say it's 9 meters per second north, 25 degrees east. I kind of like that one because it starts with the direction you're going first and you go 25 degrees east of it. So 9 meters per second north, 25 degrees east. Or you can say 9 meters per second east. That means you're traveling east, and 65 north. So I kind of like this new way. I think it's a little less confusing for students because you start with the direction you're originally traveling, which is north, and you go 25 degrees east of it. So I'm going to try to stick with these guys from now on. But this is the way I grew up doing it. I just think this guy's easier. So you will use these techniques to resolve vectors and their components throughout physics. We're going to use them a lot in projectile motion. We're going to use them when we get to forces. So get used to it. And resolving vectors and components allows you to analyze complex systems of vectors without graphical methods. That means I can give you all kinds of wacky vectors. I can give you one vector goes this way, another one goes this way, one that might go back this way, then you can go back up this way, then you can go straight up. This can get very confusing if you're trying to do it graphically, but it's a lot easier if I just take each vector individually. Like here's vector 1, 2, 3, 4, and 5. If I find the x and y components for each one of these, like each one of these has an x and a y. Find all the components, then add all the x's, add all the y's. Makes life a lot easier. So question, Jeff moved 3 meters due north and then 4 meters due west to his friend's house. What is the displacement of Jeff? And remember, displacement means how far are you from where you originally started. So in this case, we're asking for the magnitude of the resultant vector. So we draw our little axis. It says first he moved 3 meters due north, 3 meters straight up. 3 meters. And then 4 meters due west. 4 meters due west. So how far is he from where he started? This one's pretty easy. It's a 3, 4, 5 triangle. You can work it all out. 3 squared plus 4 squared, square root of that is going to give you 5 meters. So this guy is correct. And the long answer that I wrote out basically use Pythagorean theorem, and you get 3, 4, 5 triangle. Pretty easy. You could read that if you want. I'm going to skip it. Oh no. What's going on there? No. There we go. Question 2. Calculate the resultant of 3 vectors A, B, C as shown in the figure. So AX, BX, CX, AY, and CY all equal 1 unit, and BY equals 2 units. So each of these are their own little vectors. You get AX and AY, both 1 units. 1, 1. So AX equals 1, BX equals 1, CX equals 1. AY equals 1, CY equals 1, and BY equals 2. So I'm going to add all these guys up. I add all my x's, add all my y's. So my Rx is going to equal 1 plus 1 plus 1. So Rx equals 3. Ry equals 1 plus 1 plus 2, which is 4. So I get my R, vector R, equals 3, comma 4. So we can see this. Here's my Rx, which is 3 long. Here's my Ry, which is 4 long. So to get the magnitude, it'd be this guy right here. And the long drawn out answer, which I just showed you quickly. And again, it's 3, 4, 5 triangle. Pythagorean theorem, you get that. Question 3. If a vector b is resolved into 2 components, bx and by, and if theta is an angle the vector b makes with the positive direction of the x-axis, using which of the following formula can you calculate the components of vector b? So what it's saying is, I have a vector. It goes like this. It makes an angle like this. It wants to know how I can find by and bx. So to find by, if I know what b is, and I remember SOHCAHTOA, SOHCAHTOA, sine equals opposite over hypotenuse. So if I'm looking for the opposite, then sine equals opposite over hypotenuse. So therefore, the opposite equals hypotenuse times the sine. Same thing with ka. I'm going to get the adjacent equals brain fart, hypotenuse times the cosine. So these two guys right here. Can I use A? B sine theta, B cosine theta, By. Oh, no, it's backwards. I'm sorry. B cosine theta gives us the adjacent. This is the adjacent. B sine theta gives us the opposite. So it's just this guy. Sorry, it's Friday. Long day. So just part B. And here's the long drawn out answer. So just using trig, we can find all this stuff. That's it. Get some rest.